Hey everyone, Mr. Hauk here. In today's notes, we're going to look at the magnitude and direction of a sum of vectors. Let's go ahead and get started. So by the end of this lesson, we should be able to find the magnitude and direction of the sum of two vectors in different directions, and find the magnitude and direction of the sum of two vectors in the same direction. Let's go ahead and start by looking at an example about a traveling airplane. So an airplane is traveling due north at 300 kilometers per hour. Suddenly, it's hit by a strong crosswind blowing 150 kilometers per hour from west to east. Let's draw a diagram showing the direction of the airplane, the wind, and the resultant direction of the airplane with the wind. Then we're going to find the direction and the magnitude of the resultant vector. Alright, so let's start by looking at some key pieces of information from the problem. We see that we have an airplane traveling due north at 300 kilometers per hour, and it gets hit by a strong crosswind blowing 150 kilometers per hour from west to east. So, using this information, let's go ahead and try to make a picture, draw a diagram. So, here's our picture. Notice we start going north at 300 kilometers per hour. So this is our starting point. Go north, 300 kilometers per hour. Then we get hit by the crosswind blowing 150 kilometers per hour from west to east. So keep in mind, north, east, south, west. So going from west to east, here's our plane. It gets hit going west to east by this crosswind at 150 kilometers per hour. So now this creates our resultant vector, which is going to represent the sum. We go from beginning to the end. This vector started going north. This is where the start of our resultant vector is going to be. Then it ends here with the crosswind. This is where the end of our resultant vector is. Okay? Let's go ahead and write the vector component form. Now, remember, component form of a vector starts with the horizontal. Then we have the vertical component of the vector. Horizontally, we're going from west to east, so that's a positive direction, so we have a positive 150. The vertical component, we went north at 300 kilometers per hour, so that is, north is also a positive direction, so that's also a positive 300. So there's our component form. Again, 150 is the horizontal, 300 is the vertical component. In the problem, now that we have our component form of the vector, we want to find the direction and the magnitude of this resultant vector. Magnitude, well, we know magnitude. One way that we can look at this is just simply Pythagorean's theorem. Notice that this is a right triangle, so we can find the magnitude by doing 150 squared plus 300 squared equals x squared. Take the square root. That's going to give us the magnitude of that vector is 335.41 kilometers per hour. For the direction, since we have our vector in component form, we can simply do inverse tangent of 300 divided by 150. Make sure your calculator's in degrees, and that's going to give you about 63.43 degrees. Notice that since our horizontal and vertical components are positive, that angle would put us in the first quadrant, so that angle is correct. Okay, so that's a very basic example of magnitude and direction of a sum of vectors in an application example. The next one is going to get a little bit more complicated. So this one is about a day on the river. We have a motorboat on Lake Lanier is traveling at 23 knots at a direction of 42 degrees. The boat hits a wake of 3 knots moving at 117 degrees. We want to draw a diagram representing the scenario and find the magnitude and direction of the resultant vector. One thing we haven't really seen here so far in this course is we haven't been given the magnitude and direction and have to find the component form. Usually we're given something like the initial point and the starting point, and we try to find the component form of the vector from that. So let's talk about how we can get the component form of a vector if we're given its magnitude and direction. So first things first, we have two different vectors going on. We have the motorboat going 23 knots at a direction of 42 degrees. So this is a good visualization of that. So let's let the origin be the starting point. There's the magnitude, 23 knots, 42 degrees with respect to the horizontal. Okay? Now, one thing that we can do when we know the magnitude and the direction, well, we learned yesterday, or in the last class, not yesterday, but I think that was Friday, that you can take a scalar and multiply it into the vector. So we're going to let the magnitude be the scalar on the outside of the vector, and we're going to represent the horizontal component as cosine of the angle, and the vertical component as the sine of the angle. Remember that when we looked at the unit circle, cosine went first, sine went second. So this is really looking like cosine of theta, comma, sine of theta, and you multiply by whatever, magnitude that we would have out here, okay? So if we do that, if we do cosine of 42 degrees in your calculator, again, make sure your calculator is set to degrees, and then distribute the 23 into here, we would get 17.09 and 15.39. So this is our component form of this vector, the vector represented by the motorboat on Lake Lanier. Now we have this boat is getting hit by a wake going 3 knots, moving at 117 degrees. So I'm going to draw a different diagram for this vector. So here we go. Here's our vector with magnitude 3, 117 degrees with respect to the horizontal. If we write our component form here, here's our magnitude on the outside, cosine of the angle, sine of the angle. Again, calculate these in the calculator, then distribute the 3 into the vector. We get negative 1.36 and 2.67, okay? So we have both of our vectors from this problem represented in component form. Now what I want you to be able to do, and I think it's extremely important for this problem, is to be able to visualize it. So notice here in blue, this is our motorboat going at, I think it was 23 knots, 42 degrees with respect to the horizontal here. And then it gets hit by this wake at 3 knots, 117 degrees with respect to the horizontal. So we can see that it's going to take the path that the motorboat was going, it's going to put it off course. And our resultant vector, the vector that is the result of the motorboat getting hit by this new vector, is this one here in red. So notice it's going to increase the magnitude, and it's also going to change the direction because the wake is hitting that motorboat. So how do we figure out that resultant vector? Well, we're just going to notice this is just vector addition. This is the stuff we did last week. We're going to be adding this vector and this vector to get this resultant vector. So that's what I'm going to do. I'm going to add their horizontal and vertical components. 17.09 plus negative 1.36. We're adding the horizontal components. 15.39, 2.67. We're adding the vertical components. And we get that our resultant vector, which I'm just going to call R, is 15.73 and 18.06. Now we just need to find its direction. Or really, let's find the magnitude first. That's what I do first. So magnitude, same old formula, square root of the 2 components squared and added together. That's going to be about 23.95 knots. Notice I'm representing it as a decimal because it's an application problem. Then for the direction, inverse tangent of 18.06 divided by 15.73. It's going to give us 48.94. Again, we want to make sure that the direction makes sense. This is about 50 degrees. We know 50 degrees is going to be in the first quadrant. Well, if we visualize this, we have a positive horizontal component, positive vertical component. If we started at the origin, that would definitely be putting us in that first quadrant. So the degrees make sense. Okay, angle makes sense. We don't need to add 180 or add 360 or anything like that. So that's how we handle vectors when we are given the magnitude and the direction, rather than like starting and terminal point where, we would have had to do something different to find that component form. All right, let's move on to the next problem. So this one's going to get interesting as well. In this scenario, we have a soccer player shooting the ball at 33 meters per second with a direction of 28 degrees. The goalie jumps in front of the ball and slaps it away such that the ball is now moving at 8 meters per second with a direction of 178 degrees. We want to know what was the magnitude and direction of the goalie's slap. So let's think about this for a second. Soccer player shoots the ball, so this is the initial vector, at 33 meters per second, that's the magnitude, with a direction of 28 degrees, that's the direction, of course. Then we have the goalie jumping in front of it, so imagine this was the original vector. This is the soccer player shooting it. Then the goalie jumps up and slaps it away. That's what I'm representing with this green vector right here. But we don't know, the magnitude or direction of the goalie slap. We don't know the magnitude or direction of that green vector. But we do know the resultant vector such that the ball is now moving at 8 meters per second with a direction of 178 degrees. So I know the resultant vector, if I had just had, here's the first vector, here's the goalie slap, I know the resultant vector would have been this red vector right here. And I know that it's going in this direction because it's in a direction of 178 degrees. So that's almost 180 degrees. That's almost all the way around. That's why I have this vector going in this direction right here. Okay? So what was the magnitude and direction of the goalie slap? So we're kind of working backwards. We know the resultant. We know this first vector that came about as the soccer player shooting. We want the magnitude and direction of the second vector, the goalie slapping the ball away. Well, let's find the component form for the soccer player. We have the magnitude. We have the direction. Let's use what we did on the last problem. Take the magnitude, take cosine of the angle, sine of the angle, distribute the magnitude into it. Again, make sure your calculator's in degrees. And we get 29.137 and 15.493. So this is our component form for the soccer player's vector, the shot. Now let's look at the component form for the resultant vector. Well, we know that the magnitude of the resultant vector is 8. We know that the direction was this 178 degrees. So 8 times cosine of 178 degrees, comma, sine of 178 degrees. Again, calculate with the calculator, distribute the 8 in. We get negative 7.995 and 0.278. So now we need to figure out, well, how are we going to find the goalie's vector? Well, we know that the resultant vector can come about through subtraction. We know that the soccer player plus whatever the goalie's numbers had to be for the horizontal and vertical components had to equal the resultant vector. So we can do subtraction instead. The resultant vector minus the soccer player, the shots vector, is going to have to give us the goalie's numbers. So here's how I've set up the vector as a result of the goalie's slap. We have negative 7.995 minus 29.137. That's the resultant vector's horizontal minus the soccer player's horizontal. And then we have 0.278 minus 15.493. Again, resultant vector is vertical minus the soccer player's vertical. Now we can do magnitude and direction. Magnitude for the goalie's vector, just follow the magnitude formula. That, of course, is this squared plus this squared. Then you take the square root. You get 40.128. And then the direction is the inverse tangent of negative 15.215, vertical component, divided by horizontal component, negative 37.132. And you get 22.282 degrees. Now here's where we have to use a little bit of knowledge about our resultant vector, or about our goalie vector, rather. Look at the goalie vector's vector components. Negative, negative, 22.282 degrees. That's a first quadrant direction. That doesn't make any sense. We know that this would put us, if we started this vector at the origin, this would put us in the third quadrant. So let's add 180 degrees to it, because we should have a quadrant 3 angle. And that's going to give us 202.28 degrees, which makes a whole lot more sense, because if you think about the quadrants, 0, 90, 180, 270, then 360 when you go for full circle. We want to be in that third quadrant, and 202 degrees would put us somewhere in that third quadrant. So adding 180 there gets us into the right position, so that's going to be our direction. Okay. So those last two application problems, great examples of how you handle vectors when you're given magnitudes and directions, not just initial and terminal points. All right, last topic of the notes, vectors in the same direction. So on the last set of, on Friday's set of notes, we learned that in general, the sum of the magnitudes of two vectors is not always equal to the magnitude of the sum of the vectors, or in math notation here, this right here. The sum of the vectors, if you take the magnitude, is not equal to the sum of the magnitudes, okay? However, there is one case where it actually would be true. There's one case where this would equal each other. That's when the vectors have the same direction, and we mentioned this in the last set of notes. So let's see an example of this. So here's our graph to the right. We have vector u has components 6, 3. We have vector v has components 8, 4. And we have the sum, vector u plus vector v, is graphed right here. Let's go ahead and find the magnitude of the sum, and then the sum of the magnitudes. And notice that because they're pointing in the same direction, they should end up equaling each other, these two calculations right here. But let's go ahead and show it. So first, let's just look at our vectors, confirm that they are the correct components. So we can see that vector u, horizontal component 6, vertical component 3, that is correct. Vector v, horizontal component 8, vertical component 4, this is correct. So just take note of those, color coordinating of course. And if we added those vectors together, well, adding vectors, just add their components. 6 plus 8 is 14. Vertical components, 3 plus 4 is 7. Here is the sum of those vectors right there. Now let's go ahead and calculate first the magnitude of the sum. Well, magnitude's pretty simple. We're just going to take the components, square them, and add them together, and we're doing the components for the sum. So we're using these components right here. So horizontal component, vertical component, square them, add them together, take the square root. We get 245 square root of. Well, 245 is 49 times 5, and 49 is a perfect square, so that'll be 7 square root of 5. Now let's go ahead and look at the sum of the individual magnitudes. So we're going to take these two magnitudes individually, and then we're going to add them together. So magnitude of u plus magnitude of v. Well, for magnitude of u, we are using the components, so square root of 6 squared plus 3 squared. For magnitude of v, square root of 8 squared plus 4 squared. This is going to give us square root of 45. This will give us square root of 80. 45 is 9 times 5. 80 is 16 times 5. 9 is a perfect square. 16 is a perfect square. So this is 3 square root of 5 plus 4 square root of 5. And remember that when you're dealing with square roots, if the square root is the same, you can add the coefficients on the outside. So 3 plus 4 will give us 7. The square root of 5 will stay the same. Notice that this result was the same as this result. So in this case, because we had the exact same direction, notice vector u, vector v pointing in the same direction, because we had the same direction for the two vectors, the magnitude of the sum was equal to the sum of the magnitudes.